Alright, 7.3, we're going to make a small change here on the graph. And we're going to logarithmic functions. And if that's too much of a mouthful, you can just call it a log function. That would be the button that's on your calculator that says log. And if you've got your calculators that's here, if you look at it, well, it's glare. Yeah, that's the one that's on the one that we got on the board up here. That's the one right below your second button. Now, it's got log on it, so you don't have to do that. And if you hit the log button, it gives you the word with the log in it. So it automatically puts that part of it in there. So that's what we're looking at today. Now, we will talk about how to use the calculators tomorrow, because today we're going through just the setups and getting the basics on these. But we'll get to the calculator part of it tomorrow and get through everything here. Okay, so it's log functions. Now, it also could be it's log equations. Again, they're interchangeable as we're going through these. And here is your equation. Here's the basic setup on these. Okay, so you're looking at log, or the log equations, y equals, because we always start with the y equals part, log of x base b. And if you talk about a function, the only difference between a log equation and a log function is that instead of having y equals, we have the f of x equals. Yeah, logarithmic, or just say log for short. Unless you want to sound fancy, then you can say logarithmic. Sounds like a gymnastics move. What? Okay, and all these, the b that you have, that's the base of whatever it is that's the function that we're working with, or the equation we're going through. Yep, log of x base b. So when you talk about that one, b would be your base. So you'd say log of x base b. Alright, now here's where we tie this in with the exponential functions. That log functions or log equations, whichever way you want to say it here, are inverse of exponentials. So what we're going to do is basically this, is that since log functions are inverses of exponential functions, so with these log functions and inverses, they're just going to work back and forth. So here's what we're going to do. And remember, if you're talking about, when you're talking about the inverse, the big thing on the inverse is that's where you're going to switch x and y. And on that last test that we just got through doing back in chapter 6, there was that last, wasn't like the last question, but like the next to last question on the test was to find the inverse of the ordered pairs, that all you had to do was just switch the x's and the y's. Same thing on this one. Now, it's a little bit more complicated because it's an equation, but that's basically what we're going to do here. So what we're going to do is we're going to rewrite the exponential equation in log form. And what we're going to do is we're going to start with one that's just a basic, no numbers in it. It's just what it would be like we were back up here a minute ago. If we go back to what an exponential equation was, it was something like this, that you had b to the x power equals y. And we'll actually put some numbers on this here in just a second. But that's your basic, that if you do some base to an exponent, that's going to give you an answer that you're looking at. So when you rewrite these, you're actually going to rewrite it with the word log in it. Your base is still going to be base b. And all you're going to do is you're going to switch the x and y values to where it looks like it's b to the x power. Now you're going to have b, and it's not b to the y power, but I have it. So you got, again, it's not b to the y power, but it looks like it. And then the x is going to be over here by itself. So the one thing that's the same here, when you go from here to here, is still base b. Now it's a little bit lower. And you're going to switch your x and your y's. Alright, so let's give you somewhere you've actually got some numbers in it, because that's all letters. And that's just your basic of how they show you how to rewrite it without anything at all in it. That's their standard way of doing it, but let's give you one where you've got some numbers here. So let's say you got 13 to the x power equals 47. Okay, so for this one, again, you got to write down the word log. 13 is your base. And then where x is the exponent and the 47 is over here by itself, you just rearrange them. The 47 is now with the 13, and the x goes by itself. Alright, so 3 to the 4th equals 81. Okay, in this case, 3 is your base. And you've got what looks like 3 to the 4th power here. On these, again, you're going to swap it. The 81 is going to go here. And the 4 goes by itself. Okay, does that seem like that's okay? Just rewriting it on that part? Okay, and I've had people in the past, they would try to make this more complicated than what it is. And I'm like, no, it's just, you know, the bottom number that's your base, it stays the same. It's still the bottom number. And then you just switch these two numbers. So it's 3 to the 4th power, the 4 goes over here, and then the 81 goes with the 3. So you're just switching up where those two numbers would go. And about the only other thing they can do to kind of throw you off a little bit when you're going through these is just to give you something like this, maybe. Where that you take this, that they just basically put the base over here, but it's still the same setup, that you've got log of base 6. And again, the 2 now is going to go over by itself, and the 36 goes right there. Okay, and then a couple other ones, I wouldn't say they're trick questions, but some of them just look a little bit funny. You get 3 to the 0 power equals 1. Or let's make it 23 to the 0 power, just be different. Okay, so they ask you to write it in log form. There's your log. And again, 23 is your base, 0 is your exponent. So your 23 goes here, and the exponent goes over by itself, and this 1, now it goes there. And they should just ask you to rewrite it. So you're not having to solve anything with this one yet, because we're going to work on how to solve this one tomorrow, because now it's just the basic setups on how to get there. We're going to come back and talk about that more tomorrow on how to do that. Last one we'll do, and it's more of just, it looks a little bit funny. Because they throw fractions at you. Okay, so y'all kind of walk me through this one. What is your base? 2/3, right? So that one still, your base is going to be 2/3, so that 2/3 still goes at the bottom. And what's going to go right here? All right, a over 27. And then your exponent, there you go, exponent goes over by itself. Okay. As far as having you rewrite these, that's all you have to do is just realize the base goes at the bottom. Whatever the exponent is goes over by itself. The answer goes in that spot right there. Okay. And if that seems like that's okay, as far as what you're having to do with the log functions today, that's as far as they're going to ask you to go, is just to rewrite them. Not actually solve them yet, because we're going to do the solving part tomorrow, but it's mostly just rewriting so you're a little bit comfortable with them. Now, here's what they are going to ask you to do today, as far as solving goes. Is for these, they're going to ask you to go in reverse order. This time they're going to give you something in log form, and they're going to ask you to rewrite it in exponential form. And then once we do that, then they're going to have you solve it. So these should be problems that when you look at it in exponents form, that either you've got an answer jumping out in front of you, or you just think about it and the answer hopefully will pop up there. All right, and I'll show you. And this was something I remember when I first started doing all this stuff with the logs and the exponents. It's something that threw me off, because they would give me a problem like this and they would tell me to rewrite it and solve it. And my very first thing was, I was like, but there's not an equation here. All they did was just gave me this expression. So here's what I had to kind of do. This is what I had to kind of think in my head. So this is me just thinking out loud. That when they gave me this thing that was log of 16 base 4, to me it had to equal something. So I would just put that it equaled x. And once I had that equaled x, and you can let it be any number you want to, it doesn't really matter. I always just use x because that seems to be the one thing they always come back to. Once you've got it with the equals x, now you can actually rewrite it. Because now 4 is your base, so that's going to stay the same. And then you just switch these two numbers. The x goes here, and the 16 goes there. Okay, and if you're multiplying by 4s, 4 times 4 would be 16, right? And 4 times 4 is 4 squared. And since 4 squared is 16, that means that x has to equal 2. So once you rewrite it, it should be some number that when you just kind of stop and think about it, it should be something that you can go through and do that. You know, if this had been 64, then x would have been 3. If it had been 256, then x would have been to the 4th power. You know, if that had been 4x equals 4, well, then that's just x to the 1st power, so your x would have been 1. So it should be something that, you know, if you stop and think about it, the numbers should hopefully kind of come out at you there. Okay, so for the second one, let's do log of 1 base 72. Again, this is what they'll give you. So this is what you have to kind of think about. Again, that always threw me off because finally the only way I could get through this one was it had to equal something, so I let it equal x. And once I've got it here, now that part I can actually rewrite it. So again, 72 is your base. And then you just switch these two numbers up. Okay, and this was where you got to flash back to last week. For an answer to be equal to 1, what does that exponent have to be for any number? 0, right? So 72 to the 0 power, any number to the 0 power is 1, so in that case your x is 0. You know, and again, that base could have been anything. That could have been 1,720. Doesn't matter what it is. If that something the answer equals 1, then that means it's got to be to the 0 power every single time. Okay, got 2 more of these, and then we'll get some graphs we'll look at, and then we'll wrap this thing up. All right, here's the closest one to a trick question. And it doesn't look like that in the beginning, but once we set it up, then you'll kind of see where we have to kind of think about it a little bit. All right, so they'll give you log of 3 base 9. And again, to me, you've got to go ahead and think that when they give you this problem that it needs to equal to something. So let it equal x. And then once we've got it rewritten so it equals x, then we actually have to rewrite it from log form to exponential. So 9 is the base. And again, this one's even shorter because when you're switching these, once you've got your base, you just switch these 2 numbers. The x goes in the exponent and the 3 goes there. All right, now here's where we got a little bit of a problem. Got to get creative on this one because we know that 9 to the 0 power would equal 1, right? 9 to the first power would equal 9. That answer's got to equal 3. So what can we do before we do exponents on this? What can you do to 9 to get it down to 3? Screw it. Who said that? Who gave me that first answer there? Okay, so if we're going to go for these, we can square root it, right? Because the square root of 9 would equal 3. Okay, and then flash back to the last chapter. If we do square root of 9, what really is that power? That's 9 to the 1/2. There we go. So in that case, your x would equal 1/2. Okay, so if the numbers are getting smaller, you may have to square root them. Now, probably not much more than square root, but once we practice with these for a day or two, one of the next later sections, you might have to do some 3rd roots or some 4th roots. But, you know, if you think about those right now, and again, if you rewrite it and you've got some exponent you're trying to figure out, if that's 9 to the 0 power, you know that's 1, that's 9 to the first, that's 9. If that number's somewhere in between there, it's got to be somewhere in between 0 and 1. Now, just like if it was 9 squared, well, that would be 81. So if the number was between 9 and 81, the exponent's got to be somewhere between 1 and 2. It could be 1.5 or 1.5 or something like that. So, you know, if you know your basics on the properties, then you can kind of start figuring out a little bit of where at least it's got to be in the range of numbers. All right, now here's one other little thing. We'll do one more example with this to show you one thing here, and then we'll show you what the graphs are going to look like. Because sometimes when you're going through these, you're going to have a log expression or a log equation that doesn't have a base. So if you don't have a base when you're going through these numbers, because sometimes, and we'll show you one here in a second where you don't have one. If a log expression does not have a base, the base is understood to be because we count on a base 10 system. You know, to get from one group of numbers to the next, you count by 10s. You know, if you go from 10s to 20s to 30s, you're always counting 10 numbers every time. So everything that we do is based on base 10, so that's why you're going to do that. So they're going to ask you to do, so this will be like example 4. They're going to give you something like this. They're going to give you log of, now in this case you actually have an equation. You got log of x equals 2. So if they give you this one, you almost, again, here's where you have to kind of think about it. Tens your base. And once you've got it here, now you can actually go back and rewrite it. Use 10 for your base. 2 becomes your exponent, and then your x goes there. And this is actually the easiest problem we've done so far when you rewrite it, because once you put the base 10 in and rewrite it, it's 10 squared. Well, 10 times 10 is 100. There you go. So, and that's the whole thing they're trying to get you to see, is that if we were doing these log expressions, and again, we haven't used the calculator yet, but this would be a problem that you could not use your calculator to get this answer. That if you cannot solve it in log form, if you can rewrite it in exponential form, you can always find the answer that way. And if you go back to this problem back here, we'll actually show you tomorrow how you could use your calculator to get that answer. But you can also do it this way and get the same answer too. So you've got a double way. You can check your answers when you're going through this part. Okay, and then the last thing we've got to look at is the graphs. We do graphs of log functions, or again, log equations. Doesn't matter which way you want to look at it, because it's the same graph. Still 7.3, yeah. Okay, now here's the big thing you've got to realize when we look at the log functions with the equations and the graphs up here. A minute ago we said they're inverses, and we'll say it again just so we don't, just so we don't miss it. They are inverses of exponentials. And again, when you talk about the inverse, that means you just need to switch x and y. Okay, so here's where we're going to kind of flash back to the review we were doing back at the beginning of class. And this is one where you can, if you've got the basics on the exponentials, you can tell me what the graph of the log is going to look like just by doing a couple of things with it. That if we do let's do an exponential graph first. That for a domain, we said that was negative infinity to infinity. The range was from 0 to infinity. All right, you told me earlier, that point, that one point we always have with exponentials, was it 0, 1? That was kind of our key point, that no matter when we plugged in 0 for x every time. Now again, for this one, we're going to use, y equals 2 to the x power. We're going to have, so we've got a growth. Because most of the graphs we're going to look at, pretty much they're all dealing with exponential growth, so we're going to stick just to that one. Exponential decay would work the same way. It would just look a little bit different, but it's still on our same line. But we're going to pretty much stick to exponential growth here. Okay, so let's do log functions, or log graphs. And again, to go from exponentials to logs, we're just going to switch x and y. So instead of 0, 1 being our focus point, now it's going to be at 1, 0. Okay, instead of this graph, when it bottoms out here, it bottoms out close to the x-axis. Now we're going to bottom out close to the y-axis. So this x-axis, it got close to negative infinity. Now we're going to get close to the y-axis at negative infinity. And when we graphed it, it kind of chased up the x-axis toward infinity. Sorry, chased up the y-axis. Now it's going to chase up the x-axis. There you go. There's your two graphs. So exponentials look something like this. And all we're going to do is we're going to take this graph we've got here and we're just going to flip it over. So now it looks something like that. Oh, and domain and range, they get really easy. You just swap them. Now the domain can be from 0 to infinity. And your range is going to be the opposite. It's going to be negative infinity to infinity. Okay, so let's just give you, we're going to do like 3 or 4 graphs real quick. And again, we're not going to get super detailed, just a couple of sketches here. Now, and this is for log of x base b. Again, b is any number that's greater than 0. Sorry, greater than 1, because that would be the exponential growth. So if we're doing exponential growth, the base is always bigger than 1. So this could be like log of x base 2, or log of x base 3, or log of, you know, doesn't really matter what it is. This base is always going to be bigger than 1 when we're going through this thing. And we could have said the same thing back here. This is log of b to the x, where b is greater than 1. Okay, so let's give you some where you got some actual real numbers here. Again, we're not going to get super detailed, so we're not going to plot 15 points like we did on that one problem. Okay, so let's do log of x minus 5 base 4. Alright, so here's a flashback to last week. If that minus 5 is on the inside, what does that do to the graph? Which way does it move it? If you don't remember, flip back in your notes real quick. If it's on the inside of the parentheses, what does that do to the graph? Which way does it make it move? There we go. Opposite and horizontal or vertical? Horizontal. There we go. Opposite horizontal. So instead of it moving 5 spaces to the left, which is what we're thinking, this is going to be 5 spaces to the right. Okay, so if we did log of x base 4, and just kind of, you know, lightly shaded in here, that would be a graph that would look something kind of like that. But if they ask you to do log of x minus 5, again, you're going to take this graph that would normally start at 0, 1, or 1, 0, and you're just going to scoot over 5 spaces. So go 1, 2, 3, 4, 5, and then draw the exact same graph that you've got there. And there you go. There's your graph. So if that was log of x, this is log of x minus 5. You just move this graph over 5 spaces. So instead of this being at 1, 0, now it's at 6, 0. Oh, and here's a word that you haven't heard, or you thought you may not ever hear again. Vertical asymptotes. We did that back in chapter 6, you know, going through that stuff. That basically back here you had a vertical asymptote right on top of the x-axis, or on top of the y-axis, and you didn't see it. If you had this graph, they might actually have you make you go back and draw a vertical asymptote right there at 5. Because like this one, 0 is our cutoff line, and when we move this 5 spaces over, well now 5 becomes our cutoff line. So you've got a vertical asymptote at x equals 5. Because you cannot cross that line. That's your cutoff. So if you had to do domain and range here, and again, domains are x values. So we're cut off. We cannot get below 5. So same thing for domain here. 5 is your cutoff line, but you can go from 5 to infinity and pick any number there. In your range, well, it's anything. It's as low as you want to go and it's as high as you want to go. So this was negative infinity to infinity. So this will never change. The range will never change as far as what we're doing for log functions. You know, when we did the exponential functions, the domain never changed. It was always the same. So because we're flipping it, now the range never changes. It's always negative infinity to infinity. All right, 2 more graphs and then we're done. Okay, so for this one, let's do log of x plus 3 base 2. Let me kind of flip back to this one real quick. This one with the x minus 5, that was definitely inside the parentheses. Are there any parentheses on this one? No. So if you don't have parentheses, if you have no parentheses, that means the number has to be on the outside. So if you have no parentheses, that means that plus 3 is on the outside. Kind of like, can you leave the keys to your car inside your car if you don't have a car? No, if you don't have a car, there's nothing you can leave on the inside. So if you leave anything, it's got to be outside the car because you don't have a car. There's nothing that you have that's inside. So the thing they do, if they don't give you a parentheses, it has to be that number has to be on the outside. If that's on the outside, that means we're going to move this thing 3 spaces up. So again, normally we would have this graph cutting over like this. That's at 1, 0. But again, we're just going to, so if we were doing log of x base 2, we would basically be here. But because we're doing log of x plus 3, now we're going to move everything up 1, 2, 3 spaces. Exact same graph, we've just scooted it up now. Again, log of x, we're going to start at 1, 0. When you start adding and subtracting numbers, then you're going to start at 1, 0 and move it up and down and left and right based on whatever numbers they give to you. Okay, and for domain and range, did you change anything as far as the left or right movement goes? Didn't it? We just scooted it up and down. So we still got the same graph. We just scooted it up and down. So your domain for both of these graphs is going to be 0 to infinity. And your range is both of these graphs, it's going to be negative infinity to infinity. So unless you put something on the inside of the parentheses, you don't change the domain and range here. All right, one last problem, and we're done. We're going to do log of x plus 3 minus 4 base 5. And most of these graphs, they should be multiple choice right now because we haven't really talked about plugging in points, and we'll talk about that more next time of how to find the points and plug stuff in. So these, they should just give you some multiple choice. And it's more of just making sure you know where to move it and how to move it when you're going through these graphs. Alright, but again, what we got is, this 3 is on the inside. We're going to go 3 units to the left. This -4 that's back here means it's going to go 4 units down. So start with an XY axis. And again, going to need more room kind of down here than we are for the other part of it. And normally we would start with a graph like this. But we're going to take this graph that would start here. We're going to go 3 spaces to the left. So there's 1, 2, 3. Let's stretch out a little bit more. And then we're going to go down 4 spaces. 1, 2, 3, 4. So starting here, go back 1, 2, 3, and down 1, 2, 3, 4. And then we can take that graph and make it do something like that. And again, if we had an asymptote right here at 0 to start with, because we scooted everything 3 spaces to the left, now you'd have one back here that basically would cut you off at 3. So this line will be getting really close to 3 right here.